And knowing this area, there is a non-zero chance that the power goes out here. Hopefully that won't happen. If it does, well, let's, cross that bridge when we come to it.
Official technical advisor for Mops, so worst push comes to shove, I can step in and lead people on a round of why we hate thunderstorms.
Yes. Okay, I guess it's 3 o'clock, so we can get started now. This is Mops, Media Operations. If you are in the wrong place, you may have clicked on the wrong link. But if you are intending to be here, welcome. Leslie will be along shortly, I assume. Note well, you should all be fairly familiar with this by now. If not, take the opportunity to review it. If you type Notewell into IETF Notewell into Google, it will bring up something that looks very much like this, and you can peruse it at your leisure. The TLDR is anything that occurs, any contributions that occur. Anything that occurs at an IETF official meeting or on IETF mailing lists and whatnot are considered IETF contributions. So here's our agenda. Time for some agenda bashing. But we have several, I think we have 5 presentations today. Is there anything else that people would like to add or forever hold your peace? Going once. Anything in the chat? Nope. I mean, we could talk about Kate Bush, but
Jake. Yeah, heck. Was I supposed? Oh, there it is. Yeah, second slot. All right. Never mind. I didn't see myself.
Right. I've got your slides. Don't worry. Believe me, I would have bugged you if there was something missing. Oh, are you saying that you weren't sure whether you asked for a slot or not?
I thought I was. I hadn't looked at the agenda. I hadn't finished reading it, and so I didn't see the second slot, and so I was a little. And I thought it was 10 minutes. Just a minor point of confusion. Sorry about that.
Okay. Do you need more than 10 minutes?
Hopefully not, but
okay. Yeah. Welcome, Leslie.
Kind of thought the calendar item would have the link in it. Curiously.
Oh, interesting. Yeah, no, I just went to the IETF 111 agenda. But at least we don't have to play, magical logins with WebEx. It just recognizes my authority as chair, supreme authority as chair, when I log into MeetEcho. Anyway, we just did the agenda bashing, so I guess.
And we have noted well.
We have noted well. The next 2 things are, of course, our favorite part of any working group session, which is we need a Jabber Scribe and Minute Taker. I'm perfectly happy if multiple people contribute to the minutes. If for instance, speakers or people who are otherwise participating in the meeting can take minutes when they're not otherwise distracted by either presenting or contributing, then as long as we have multiple people, we'll make sure to cover everything important. So can I get some volunteers? All right, Jake said he could take minutes except during his own slot. Can we get somebody to take minutes during Jake's slot? Come on, don't be shy. I can wait all day. In fact, I think we've got some extra time, so we literally could wait all day. But
You and I, Kyle, had some discussion about what it entails to take minutes, and we acknowledged that having the video stored on YouTube really does take away the pressure of capturing every single word that somebody says. But it would be helpful, particularly because the automatically generated transcript in those videos maybe not quite so up for keeping track of technical jargon and whatnot. It would be helpful if we had hands who could help capture the high points and in particular capture points around particular technology terminology. So thank you, Jake. And are there any
And
other volunteers?
Spencer suggested that he is willing to take minutes during Jake's slot. So thank you, Spencer. So I think we're covered. Now we just need Jabber Scribe, although, I mean, Jabber ends up in the chat here, right? So it's just if somebody wants something announced at the mic, I mean, to be perfectly honest, I could probably take that. So I will anoint myself Jabber Scribe.
Okay.
All right.
I'm trying to copy and paste the URL for. There we are. I put the URL for the CodeMD stuff into the chat in case anyone else doesn't have it handy. And we are not doing milestones yet.
Oh, right. All right. So now we will switch to the Streaming Video Alliance slides. Give me a moment.
And do we successfully have Brian here?
Yeah, I was able to join. Thanks for all your help getting it set up.
Great. So just while Kyle is pulling up the slides, I'll give a little bit of context here. The Streaming Video Alliance Network and Transport Working Group has been working on a document around considerations for video around 5G and 5G access. So there's an awful lot of expertise there, an awful lot of interesting considerations. And I thought it would be interesting to have Brian give us a sort of a flyover of sort of what are some of the aspects of 5G that are of particular interest when it comes to delivering video and any lessons learned along the way. So with that, take it away, Brian.
Okay, thank you, Leslie. So as Leslie said, we've been working at this in this document at the SVA for probably the better part of a year. We've had a number of clearly some very smart people working on it, from vendors through to the network operators themselves, through to the caching companies, and even the public cloud providers have contributed. So hopefully we've got something that's fairly good. It covers what people should know, or at least should be considering when they're looking at 5G and delivering content really over that 5G network. So next slide. So really, if you ask people what are the key drivers for streaming media, it's always, in many cases, it's always more. So it's really more bandwidth. They need more and more capacity to deliver better quality content. They need less latency to actually make that experience a little bit more responsive. And they really need massive scale access. So they need to be able to connect devices, multiple devices, really to that 5G network to be able to consume services. And it could be anything from fixed wireless access within the home, through mobile devices, to even the connected car. And if you look at some of the car companies, they're actually building out their own infrastructure to deliver entertainment and gaming, really as part of the package that you get or you can subscribe to when you purchase a car from them. And so there's a number of things within 5G that really helps. There's all that additional spectrum that 5G brings. There's really enhanced radio connectivity. And then there's a whole 5G cloud and the 5G video edge stack that can actually help contribute to improving the experience for users. And that's some of the stuff that we did look at really within the document. Next slide. So clearly one of the biggest things with 5G is really improving access. And that's actually done through a lot of spectrum consolidation and really auctioning off a lot of the spectrum that they freed up from sort of terrestrial television services and other spectrum that really was available to deliver these new services. And really, if you look at the increase in spectrum, or the increase in bandwidth that comes with spectrum, it's actually quite interesting, because if you look at LTE today, and I don't like putting numbers to a particular device or to a particular session, but if you look in general with LTE, you're probably getting about 1 gigabit per second delivered per kilometer squared. When you actually look at the sub 1 gig bandwidth, which is effectively the LTE spectrum for 5G, that increases by 10 times. So it jumps to 10 gigabits per second. 5G centimeter wave or sub 6 gigahertz bandwidth increases that by 10 again. So now you've got 100 gigs per kilometer squared to service those customers. And then when you go up to sort of 5G or millimeter wave, you're now looking at least 1 terabit per second. Potentially, it's even more, in some cases, and it depends who's selling this stuff, but in some cases, they're claiming up to 10 terabits per kilometer squared of bandwidth that's really available for applications. And so really, when you begin to look at 5G and you begin to look at sort of the millimeter wave deployments that are going on, there's effectively 1,000 times more capacity than really you're seeing with sort of traditional LTE that we have at the moment. And again, millimeter wave seems to, at least for media and entertainment, really seems to be the most exciting because potentially you can actually get up to 10 gigabits per cell site, obviously shared. You can get extreme low latency, so less than 4 milliseconds round trip time on the network. And for things that are interactive like XR and VR, that makes a huge difference really in the user experience. Unfortunately, it's fairly low coverage. You only get about 250 meters per cell site. But one of the interesting things with that is that you get a lot of spectrum use because it doesn't propagate that far. That spectrum can be used over and over again, really leading to sort of massive scale. Next slide. So additional spectrum really won't do this on its own. You need some enhanced radio connectivity to go along with it. And really, as part of the 5G radio network, a lot of the connectivity has been redesigned. I mentioned sort of, pardon me, millimeter wave. And again, millimeter wave is really deployed as these series of small cells within a mesh. And effectively, every 250 meters in urban areas, and it really forms this dense network or dense mesh that provides exceptional connectivity. And I always like to think of it really as a way that sort of bridges Wi-Fi with cellular services. So from the construct of the mesh, it's more like a Wi-Fi network, even though it's delivered really as part of the radio network from the content or the communication service providers. MIMO or multiple input output on the antennas is another big thing. And with LTE already supports MIMO. But what they've done is they've really increased the number of antenna ports on these antennas. And they've actually sort of, instead of supporting about 8 to 12 antenna ports, the new set of antennas really support around 100 antenna ports, and it really increases the volume of the number of network users that can connect to any of these antennas. And so, it does that by a factor of around 20 to sort of 25. And it really makes massive scale access something that's now achievable, because you can have so many multiple devices and applications connecting to these networks all over the same site, that it makes it worthwhile, even on a television or a computer or whatever, to actually build in a 5G modem or 5G connectivity and let that device connect directly to the network itself. So it massively improves the number of devices that the 5G network can support. Clearly, one of the drawbacks is really things like cross interference. So you've got a lot of density with massive MIMO, and you can get crosstalk really in all those channels. But they've implemented beamforming, so similar to what you would get with the Wi-Fi network within your home. So the network now orchestrates packet delivery. It's really not just sort of pray and spray. So it avoids objects, and it avoids cross interference with other signals by really targeting the beam to the device, even if it has to bounce it off walls or other sort of structures, and really optimizes that path and really cuts down on the interference. And sort of finally, clearly today with LTE, it's like using a walkie-talkie, so you can either transmit or receive on that connection that you have with the cell site. With 5G, it now becomes full duplex. So you can transmit and you can receive on the same frequency at the same time. And so it really optimizes the delivery, particularly of content, where it's an interactive content, where it's actually required that you can do both. You can both transmit and you can receive really at the same time. And so this sort of enhanced radio connectivity is really the essential enabler of ultra capacity on the 5G RAN. So combined with spectrum plus all these new technologies, it actually gives you a lot more bandwidth and a lot more capabilities for delivering content services. Next slide. One of the other key things, and I've worked actually quite a lot on this at both Ericsson and Nokia, is really this sort of concept of a converged 5G edge. And so, Nokia obviously has their own flavor of it. They've been the one really championing the ETSI standard around MEC or multi-edge compute. The large public cloud providers are also providing solutions in this market. So AWS has the wavelength infrastructure that's already deployed in a number of different operators. And so effectively, this converged edge 5G cloud really provides compute sitting at the edge of the network for applications that require real-time performance. Globally, once they get this stuff deployed, there's going to be thousands of these sites, and each one of these sites will actually be will have from 1 to 5 milliseconds latency. So, particularly for applications like XR and VR that are highly interactive, it really optimizes the experience, and it really makes sense to begin placing these functions or these workloads really at the edge of the operator network to provide a much better quality of experience really for the user. Again, Amazon and Azure are already deploying in the aggregation network within the operators. You have multiple applications sitting that require near-time performance. And again, there's thousands of sites currently being rolled out. A key part of this workflow is that a lot of functions will actually migrate to the edge. So functions that require massive data throughput, that require low latency, that require data sovereignty, are all moving really down to the edge of the network. Again, providing low latency, providing terascale, letting a lot of devices actually connect and utilize those services sitting at the edge. And there's a lot of software-defined video functions that are now migrating from the device up into the edge cloud. So a great example of that would be something like XR devices. Clearly, they want to make these devices really as small as they can. They want to make the batteries last as long as they can. They want to make them all-day wearable. They want to make them as cool as possible. So really having a large headset and walking around is something that people are not, it's not something that people want to design devices to do. They want to sort of minimize it and make it really look more like a pair of glasses. And so effectively moving a lot of that functionality out of the devices really into the edge, having the edge render a lot of that video, having the edge make a lot of the decisions, perform a lot of the compute that actually goes with those workflows for delivering XR content really makes a lot of sense. And then streaming the final result down to the user device or the user wearable where it's simply rendered really begins to optimize those workflows. And I think when you look at this, and particularly when you look at the rollout of XR, more and more of that functionality is actually being moved up into this converged 5G edge cloud. And you know, it's really, I think, setting the stage for new models or new distribution models for both streaming and for XR services. Next slide. So to go along with that, we actually have a new 5G video stack that's being sort of contemplated, it's being deployed, and it's being delivered really now. If you look at Nokia, they actually have their own 5G video stack. They're actually pushing with a lot of their deployments. And really, they've sort of taken a lesson from the public cloud providers. You know, if you look at the lower levels, you have platform as a service. You obviously have ETSI-MEC, and there's a number of private cloud and public cloud deployments that are actually happening to support these video functions that sit above that. At the next layer, you have a set of platform services. These tend to be sort of big data services, you know, around analytics or orchestration or inference. You know, it's applications that are already being provided by people like Azure or people like AWS. Or for analytics, it's open source applications like Hadoop, but they're really being deployed as part of the platform service for this 5G video edge stack and effectively being leveraged by all the applications that are sitting on top of that. So typically for analytics, there won't be different sets of Hadoop instances or databases that are actually collecting this. Typically, people will actually use the same instance. It'll be multi-tenant, and they'll be able to extract and analyze their own data really as part of that. Above that is really the applications. And if you look at the video applications, they're becoming more and more modular. So to contribute video, to distribute video, even to do things like time shift or advertisement for monetization, it's really, the architecture is really changing in terms of how this stuff is being deployed. There's really no more large monoliths that are driving this. People are migrating more and more towards sort of disaggregated applications, really looking at small capacities or small capabilities that are actually orchestrated. And again, it's very flexible, it's very future-proof, and they're actually beginning to leverage things like CI/CD, DevOps, and other sort of, I would almost describe them as culture changes to really push a lot of this stuff out. And, you know, arguably Amazon's been doing this for sort of 15 years, but I think for the telcos and really the CDN providers, this is really sort of their first foray into this infrastructure. And I think when you begin to look at it, I mean, the models there, it's actually been proved by a number of these large cloud providers. And I think ultimately it really gives the streaming vendors really so much flexibility to deliver services and to customize and sort of tailor services and to provide those services really at will and to be able to scale them at will. That, you know, effectively it really enables this vision of the 5G video stack and the 5G cloud and sort of ties them together. So I think ultimately when you see this rolled out, and there are some pieces of it rolled out today, but it's going to be highly elastic, it's going to be highly scalable, it's going to be available at will, and particularly for the content owners, they're effectively going to pay for what they use. So they don't need to actually have dedicated boxes, they don't need to set them into an operator infrastructure, and they don't need to be paying for rack space, for cooling, for power on a 7/24 basis. They're actually going to take bits and pieces of this infrastructure and they're going to use it really as they require it. Next slide. So there's two other important things really to consider when you begin to look at these video applications. One is vertical scale. And, you know, clearly there's no right place in this sort of edge to cloud stack to run a video application. It really depends on the functionality. So if you have applications that are making bespoke content, that are doing highly tailored or highly personalized content like advertising, it makes a lot of sense to put those down as close to the edge really as possible, and get them right down almost one hop from that end user. If you're looking at applications such as, origin services or content creation, really does make a lot of sense to put those at the edge. So you're probably going to see those really deployed more sort of at the public edge. So the likes of Lumen or Akamai, or even in the public cloud and hyperscalers, so Amazon and Azure again. And so when these things are being deployed, what we're actually seeing is we're having these sort of cooperative distributed functions throughout the network. And so, highly functions that are doing highly personalized content sitting down at the edge, while up in the public cloud providers are still doing a lot of the storage, a lot of the archive for content. All of the origin servers are still sitting in there. And effectively, these applications are really sharing their state, their analytics, they're sharing runtime information to make it a little bit easier and scale a bit better, really across the stack. And then it really allows, certainly in times of peak workloads, to actually scale by provisioning up the stack. So if you don't have enough resources sitting at the edge of your network, and potentially a service can actually, absorb a little bit of latency, you can now begin to deploy those or redeploy them really in the core network or really in the public edge to provide massive scale. And so that's certainly one of the things that I think is worthwhile considering for video applications, and it's certainly, I think, one of the things that's going to scale it globally across multiple operators. Next slide. The other thing to consider is horizontal scale for 5G, particularly when you're looking at mobile applications. And I'm not going to go too deeply into this because it's I've done it in other presentations. It sounds like opening a can of worms. But there's really a number of different scenarios that content owners have to consider. If you're driving in a car, your kids are consuming content in the back seat, and you're moving from cell site to cell site, clearly you need this sort of concept of inter-edge handoff. And so as you move from cell site to cell site, obviously you could still be using the same edge pop, but you need that layer of orchestration that actually moves that tunnel or that session from one cell site to the other cell site to the other cell site, and effectively connects it back to that edge pop and the application within the edge pop itself. Inter-edge, and again, if you look at Nokia and Ericsson, this is something that they're working on today, is where effectively you're moving from cell site to cell site, but you're also moving around from edge pop to edge pop. And so one of the key things there is to be able to actually take the application, to take the session state that you have, to take the data that's actually archived with that session and move it from one edge pop to another. And there's really a number of ways that people are looking at doing this. One of the concepts within MEC is that you take that whole object that the user is interacting with, so complete. So you have the runtime, you have the state, and you have the data, and move that whole thing as an object. If you look at functions like Lambda and serverless, effectively that data is archived. So you can actually just spin up that Lambda function really on the other edge pop and really import the data. There's a little bit of a hit there, because obviously there's a cold start, but effectively it's another way of doing it, and it's something that's actually being used today if you look at service compute in a lot of the large cloud providers. And then sort of the third one here is really this inter-edge, or different version really of inter-edge, where if I move from one edge pop to another, that edge pop may not necessarily be cloud enabled. There may not be an application there that's available, or compute services that are available to actually run my application on. So in cases like that, they can certainly fail up the stack, into the operator core network or really into the public edge. And if the application can actually absorb a little bit of latency, that's a really good way to do that, because I get my session continuance. There's no interruption in the video, but it's running at a much higher tier or a much higher level within the network. And again, that session continues, and as a user, I really don't experience much of a hit as I'm moving from edge to edge. And so these are really some of the things, particularly around mobility, that need to be considered. And again, as I said, there are a number of different ways to do this. I mean, clearly the large telecom vendors and the radio vendors have a slightly different approach than the cloud vendors. But I think ultimately what you're going to see is them both coming together and providing really a solution that leverages the best of both, I would say. So being able to kind of use serverless really within conjunction with the core networks and the eNode Bs as a control plane and mechanism to really drive that. Next slide. The other interesting thing about 5G is that, with LTE and implementations before that, you effectively had appliances that you would go to a telecoms vendor and buy. That's changing quite a lot within 5G. The infrastructure itself, both for the network and for the edge cloud, is becoming actually very agile. It's becoming virtualized, and everything is now being driven through network function virtualization. And so really there's three key parts to deploying that. There's the actual infrastructure, or the NFVI, that actually sits below that. It's generally comprised of COT servers, off-the-shelf storage, off-the-shelf switches that are virtualized really as appliances that you can now take your platform services or your application functions and begin deploying them on top. It's driven by this management and orchestration layer that provides a fair degree of self-organization really around that. So basically, and I think I talk about it in another slide, but basically the whole premise behind 5G networks is that effectively, it's going to be based on an NFV platform. It's going to be self-organizing, so you're going to have an orchestration layer that actually does all the lifecycle management. It's going to distribute functions. It's going to scale those functions at the edge of the network or within the network. So again, it's just going to be more like an Amazon instance rather than what you've traditionally got from the application vendors. Next slide. And again, I sort of mentioned a little bit about networks being intelligent and self-organizing. So if you look at sort of a slice through these networks, you obviously have your orchestration layer that's going to organize the 5G core, backhaul coordination, and the edge cloud itself. Plus, you have all the radio network coordination itself. The orchestration layer is actually going to be able to optimize that. So it's going to do a lot of the troubleshooting, detect anomalies on the network, and be able to sort of address those. It's going to provide coverage, QoS, capacity optimization. So for things like congestion control, that's really going to be organized. You're going to be able to do things like really organize that on the fly and be able to use new protocols like PCC to be able to actually deliver that and to be able to tailor that for the type of application that's being pushed out. And then clearly scale and resilience, being able to sort of configure these networks really as required. And so at a high level, a lot of these networks will be self-healing. They're going to be self-optimized, so you're going to get the best quality of experience you can out of them, and they're going to be self-configured. So they'll know the best place to run the functions, they'll be able to deploy the functions, and they'll be able to actually manage that on behalf of the operator. And a lot of that will be driven from things like machine learning and inference and stuff like that, based on the data that's actually coming back from the network or the applications that are out there. Next slide. And again, you know, it's definitely going to be a lot more agile than what you're typically used to seeing. And you know, on the left-hand side here, I've sort of given a little, it's just a little overview or a little comparison of, you know, looking at a plant. So to deploy a plant it really is sort of a 6 to 7 month process. You know, you have to buy it, install it, rack it and stack it. You have to test it and do that sort of thing. When you're looking at deploying applications or new services in the cloud, you know, effectively it takes me about 11 seconds to spin up an instance within Amazon. And so from that perspective, you know, things will be a lot faster. It'll be a lot more agile. You know, time to market can be reduced substantially. You know, we've definitely seen a massive reduction of around 80% in getting new applications out into the field. And then in terms of reduction in time cycles to deliver applications, you know, that can be reduced by about 90%, really because you're not updating servers, you're not spinning up new environments, you're really not deploying this stuff and testing it. A lot of it is already there, and it's simply just a question of using it. And really because of that, a lot of these relationships that the operators have had with the traditional vendors are changing. You know, I still think Ericsson and Nokia, you know, they're probably going to be the only game in town to go to and buy your radio networks from. But really, when you look at sort of the compute and really the platform services that go along with that, it's definitely going to be more of the hyperscalers, the open source communities that's really going to provide that. Next slide. And then sort of, you know, some of the other things to sort of consider, you know, I mentioned congestion control. You know, clearly people typically today will deploy a Linux box and they'll actually use TCP, typically cubic, really as part of that. And there's a bunch of issues, particularly when it comes to mobile. You know, the spectrum, the share of the spectrum that's available to you changes a lot. You have these deep packet buffers that are problematic. And then you've even non-congestion loss that's inserted there. So if you run out of bandwidth or data on your plan, your operator may actually throttle you to do that. Things like performance-oriented congestion control can actually help that quite a lot, because it does allow you to effectively tailor each application that you're delivering over the network with different parameters really around the congestion control. So if you think of things like you know, video conferencing and streaming, they need very different things. Video conferencing has to be very low latency. Streaming, you know, you need to deliver massive amount of data to actually provide the best quality of experience. So these things can actually be configured, tailored, and adjusted on the fly, and it fits really well into that sort of 5G model of virtualization and self-optimization. New protocols, you know, people are actually doing a lot of experimenting with QUIC, which is an IETF. I think the rec was actually just released back in May. You know, and really it does things like, you know, optimize the connection setup. There's no head of line blocking. So effectively your video content and the content that's important to you can actually bypass a lot of the other stuff that's actually happening on that connection. And you actually get better transitions between cells and networks. You know, effectively each QUIC session has its own unique user ID, and it almost brings state, I guess, to the protocol. So effectively it allows you to actually transition from network to network, from IP address to IP address, and it really makes that very seamless. And then, you know, Anycast is already being deployed within the 5G network, you know, so you have multiple servers with the same IP address. BGP protocol routes you to the one that's kind of most appropriate based on you know, latency or load within the server, or even cost. And this effectively helps really distribute that workload and distribute the sessions really to the best place within the network and the place that can actually serve those sessions better. Next screen. And then really just some of the M&E use cases that are already being trialed in MG on 5G. So clearly, you know, enhanced OTT, they claim is really the killer use case. 70% of the data within the next sort of 3 or 4 years will actually be media that's actually being streamed. both to a mobile device and to the home with 5G fixed wireless access. FEMBMS is really the enhancement to EMBMS. So again, it gives you that ability to actually broadcast content. And then network slicing really allows operators to actually buy, or content owners to buy a piece of the operator network to take this virtual slice that effectively guarantees them really, really good QoE when they're delivering their content to users. Cloud gaming is another one. Again, gaming is a lot of the processing and rendering is actually done in the cloud and streamed. And it's very applicable to XR and VR experiences when you really want to offload a lot of that stuff from the device. And so it really makes this available to sort of cheap, low-end devices without having to go out and spend, $6,000 to $8,000 on a dedicated gaming rig. Connected cars is another interesting example. There's 2 or 3 of the large car companies in North America that are already building out their own CDNs that they're going to provide as a paid service when you actually purchase their car. In-venue experiences, so being able to actually take XR and mixed reality and actually stream that to a user as they're sitting in their seats, so they can get updates and they can get metadata. They can actually see what the batter's last 6 at bats were against a particular pitcher. So having all that additional metadata and additional information in the stadium is something that's definitely a use case that people like Major League Baseball and the NBA are looking at. And then sort of finally, content contributions. So you have things like, news gathering, citizen journalism. A lot of this is actually being uplinked using 5G, and there's actually 2 companies on the market that are providing a platform that will allow people who are in the middle of a protest or whatever to effectively go live and begin to stream their own content that can be picked up, either by sort of traditional outlets like CNN, or sort of more of the new media outlets where it's actually being streamed over YouTube and stuff like that. Next slide. And sort of, finally, one of the things that we've been thinking about is, will 5G challenge the status quo? And again, it depends on who you're actually buying this equipment from. Obviously, FEMBMS could potentially be a competitor for ATSC3. It provides for 8K capability to deliver content. It supports all the standard streaming formats. It's generally codec and packaging agnostic. And it also provides things like free-to-air mobile reception on devices without a registered SIM. So on a television set, effectively with a 5G receiver, I can actually begin consuming my content services really over that television set if they're being delivered over the mobile network. Personally, I think it'll be a little bit different. I think these services, there's a lot of synergy, and I think you're going to see a lot of hybrid cooperatives. So, ATSC3 will probably be the primary channel that you consume your content on, but anything personalized or bespoke will actually be delivered over the 5G network. So it could be multi-views, different camera angles. It could be catch-up. It could be rewind. It could be a way to hyper monetize content that's actually being delivered with very targeted advertising to your television. And I think there's a lot of utility functions that were already, if you look at Nokia and Sinclair, they're already beginning to experiment with this stuff. So things like Title VI compliance. So effectively, if I'm watching a television program and there's someone on the screen actually signing what the presenter is saying, it's very intrusive, sort of, if you're not hard of hearing. But for someone in the family that's hard of hearing, they can simply just put on a set of XR glasses, and they'll have that person standing right beside the television, signing what the person is saying. So I think you're going to see a lot of these side services, a lot of these utility services that are actually going to be used to actually enhance ATSC 3.0. So from my own perspective, I don't ever see 5G replacing traditional broadcast. And final slide. Again, as I said, we've been working on this technical brief probably for over a year now, and really it's a way to provide really an educational resource to let people know the capabilities of 5G, to let them know how applicable it is to streaming, and to really let them know some of the pitfalls if they do decide to go ahead with that. And you know, from our perspective, you know, we're really looking at the technology. There's no business case. There's nothing like that in there. So it really does, for a content owner or for a communication service provider, it really does provide them, I think, with a very high-level overview, just outlining the benefits, outlining the technologies they can potentially use, and really giving them a place where they can actually start and begin sort of kicking the tires when they're considering delivering media over 5G. And I think that's it.
Great. Thank you very much, Brian. So I think we have a few minutes left for any questions. I think it was a really interesting presentation, and I hope people got that perspective of, you know, not just the technology, but what it might support. So any questions for Brian? Go ahead, Jake.
Hi, Brian. Thanks. That was interesting. There's a couple of things in this space because I think you talked about a lot of the promise that I've seen referenced for 5G. But there's a few things like when the service operator picks their congestion controller. Are there any provisions you've seen emerging during this research about like how to prevent providers from sort of picking congestion controllers that just make theirs faster at the expense of others?
Yeah, I mean, that's actually a very good question. I mean, certainly some of the things that we've been looking at as part of this are really methodologies like PCC, so performance-oriented congestion control. PCC is, unlike Cubic, it's really highly configurable. So you can actually tailor that for a particular use case. There's really two parts to the PCC infrastructure. One is really the basically a utility function that is really looking at the network. It's looking at sort of loss, latency, and stuff like that, and it's really creating what they call a utility score. And they can use that utility score to actually then have a rate selection algorithm within the caches, decide what rate to use and stuff like that. The nice thing about it, though, is you can have actually multiple utility functions. So it's not a one-size-fits-all like Cubic. You know, basically that utility function can be tailored in many different ways. So you can have policy around things like you know, video conferencing where you want extremely low latency. You can have policies that actually manage the streaming part. So you're actually looking at delivering very, very high quality video, perhaps at the expense of some latency. And so it's very highly tailorable and highly configurable. So by implementing stuff like PCC, it actually gives you the ability to adjust the rate control really on the fly. And you can actually adjust it on a per service basis. And again, you know, since it's being managed by the utility function, it actually knows about all of these other services that are actually sitting on the network, and they can actually go out and play really nice together. And you know, it's from my perspective, it's something that's actually very, very interesting. I think exciting for 5G.
Sure. Okay, so you're saying that the sort of you know, I guess I don't know what you call this, the deeper edge cloud sort of operators would be providing a sort of interface for real-time bidding for the desirable traits or something for the services that are running on top of it, or
Not really. I mean, I think there's 2 points to your question there. I think it's really being deployed. The PCC is really deployed as part of the Linux operating system or whatever you actually happen to be running that on. So effectively, it really just replaces TCP cubic that's there today. But it gives you a lot more flexibility when determining the services and determining policy around those services. The other thing too,
so the services will sort of pick what they think is right.
Exactly, and the other thing too, when you look at edge, edge means a lot of things to different people, and the last mile means a lot of things. So how you want to configure something that's really sitting at the side, at the edge of the operator network, or really down at the cell site, maybe something a little bit different than what an Akamai or a Lumen might do, that are actually paired with the operator network. So again, PCC gives you that ability to actually dynamically adjust those rates and the rate control based on your location on the network as well. Because clearly, if you're paired with the operator network, you're going to get a lot more packet loss and latency than you would if you're sitting at the edge.
All right, thanks. And then the one other one I had, if there's nobody else I'm in front of there, is like you said it would be kind of like an AWS instance, sort of a setup with the managed service deployment, as I understood it. And I was wondering, like, the cloud providers, usually you're kind of explicitly picking which data center you're going to run in from a relatively small-ish pool. And I was wondering if it sounds like with these 5G deployments, you're going to have a lot more locations. Is there anything again in the course of this research that you've seen about like how that will be interfaced, or is that just sort of up to the service operator to figure out?
No, there definitely are going to be a lot more data centers really deployed at various tiers within the operator network. And again, both the ETSI-MEC implementations and the service operators are really sort of adopting the same approach. They're going to really attempt to run that function, as close or in the best possible location, really for the client to access it. And so for streaming media, having it right at the edge of the network really makes sense to sort of get low latency and data throughput and stuff like that. But the ability is there really to not feel up, but to actually deploy up in the stack. So again, if the edge is really busy and you can actually go up to the next tier and add maybe a little bit of latency, they're actually going to deploy it up there. Or if you actually need global coverage or broader coverage for a particular application, they can actually deploy that higher in the stack as well. So the layer, when you're actually orchestrating this, the manual layer really has a fair amount of intelligence, really where to decide where to run this, not only based on the performance requirements, but really based on location and really based on things like how busy that edge is at the minute. Maybe it's not possible to deploy it there.
Okay, great, thank you.
All right, thank you. One question from me. I'm a little curious if you have a timeline for when the SVA 5G technical brief will be available.
It should be available within a couple of weeks. We're
Great.
just going through one final edit at the moment, and as soon as that's done, it's actually going to be published. There's a placeholder already on the website for it.
That's great. I'm sure that the Mops working group would love to have a pointer when it's available, so I'll put it in my diary to make sure to share that. Great. Thank you very much, Brian.
You're welcome.
As a note taker, I hope it's okay. I went and searched for a link to it. It looks like that'll be a stable link, but yeah,
Okay,
we'll update
great.
the notes if that changes.
Yeah, that
Perfect.
is the link for it. So.
Awesome. All right. Thank you much. And Kyle is getting us ready for do. So Jake, take it away, please.
Right. Hi, I'm Jake Holland. So we've been working on the streaming opcons draft. Go ahead to the next slide. I'll be just giving an update on what we've been doing. This is a visual representation of sorts. You can see that since our last meeting has been the bulk of the recent work. We think it's close. We go ahead and go to the next slide. We think so. There's a few remaining open issues in the repo. There's actually one brand new one from I think 2 minutes before this meeting or so. That was a suggestion from Mike English as part of the work that we're doing on the advertisement section. So we think that this is our sort of initial proposal of how to categorize these things. What we'd like to do is we think the advertisement section and its impact on streaming considerations is actually pretty important to get in there. The rest of them, we're kind of thinking like we will do what we can. We'll maybe take something like 2 weeks and then go to last call, even if we end up dropping these. And that's, I guess I would invite comment on whether you think these are right or not. The new one, by the way, was it's regarding segment size and keyframe intervals. Just a sort of in passing suggestion that came with some of the text from the sort of proposed advertisements section. And that might be worth including, but I've tentatively slotted it right under the further reading in the non-blocking section. So I can give some updated slides for the records on that. And I guess if we don't have anyone commenting on that at the moment, we can also include the next slide. There's one other issue that I've listed there, which is likewise an outcome of a recent workshop that Ollie brought. This is about cloud-based encoding, packaging, and origin workflows. There's some really interesting ongoing work. We think it's very likely to be relevant to operational considerations for streaming, but it's kind of early days, and we don't think it's solid enough to dig in very deep. There might be something we could say, which I guess I would include in maybe a nice to have that's just a sort of pointer to the few resources that are out there. And I mentioned that it's worth researching, or maybe we'll just sort of, if there's not enough there, then we again could just go on without it. We don't think it's developed enough to really put a lot into it, and we don't think we should hold up this doc waiting for it, probably. So yeah, that's kind of where we're thinking right now. What we'd like to do is, I guess the next slide, that is where I have that, is move to last call in 2 weeks, after one last chance to see if there's any issues we get inspired to clear out, and to finish up the ads, and then just do the last call and hopefully have that go through cleanly. I guess I'm interested if anybody has been keeping up with the changes. There's been a lot of them recently, but we think we're almost wrapped up. And failing any input, I guess our plan is to just go ahead with that proposal. So that's my last slide, and I will just invite comment.
Yeah. So I would particularly like to hear people's comments. I think that you've articulated the list of known remaining issues in the documents in your plan for dealing with them. I think even reactions in terms of whether people think that these are reasonable approaches or not would be helpful at this point, so it doesn't leave you feeling like you are talking to dead air. Perhaps I should have planted a question. Glenn.
Generally, Jake, feedback is I think it's going in a really good direction, and I have been watching. And when you guys do your commits, my inbox blows up, so I can tell when you and Spencer are on the job and Alec doing stuff. But I think it's gone in a really good direction. And other than that, I don't really have any changes, of course, to suggest. You're doing well. Thanks.
Great, thank you. Always nice to get a vote of confidence,
Great.
especially from
All right.
Glenn.
Well, you know you earned it. Yeah. All right. So we had talked about doing the last call for this document in this time frame, and it sounds like, you know, we are more or less on track for that, given your plan for handling it. So I think that
We are
absent any
proposing
other,
to be 2 weeks late,
Yep.
I think, but
well, I said more or less. In the context of the milestone discussion that we can have later, I think that in pretty solid shape. Yeah, so I guess I would ask for sort of going once, going twice. Are there any other comments from people? Thumbs up, thumbs down. Can't wait to see it in print. Don't save your comments for when it's actually in last call and then give Jake grief. I will refer to the attendance list during last call to make sure that people aren't chiming in too late.
suggestions that make the document better are welcome, even during last call. I will say as an author.
I mean, you know, if we go back to this slide, right, this is a good illustration of when comments tend to come in during the life cycle of the document.
All right.
So, I mean, I'm just saying, you know, reality.
So that's all I got, and thank you.
Great. Thank you, Jake, and co-authors. All right. Rena, were you looking to make a comment on the document, or are you getting lined up to present?
Getting lined up to present.
Okay, great. Thanks.
Did you want to drive, or did you want me to handle the slides?
It's fine.
Sorry, you cut out there.
Yeah, you can drive it. It's fine.
Okay.
Thank you. Hi, everyone. My name is Renan Krishna, and I will be presenting an update to our draft. This is a joint work with Akbar Rahman. Next slide, please. So updates to the draft are in section 4. We have also made editorial changes as appropriate throughout the draft. We will talk about these changes in the next few slides. Next slide, please. We got very helpful comments, suggestions, and questions at the last working group meeting and have incorporated them as updates to the draft. The updates are in form of a discussion on the allowable time budget beyond which the problem of motion sickness caused by motion to photon delay occurs. So let us take a look at these updates. Next slide, please. One of the requirements for our use case is that the display on the AR/VR device should synchronize the visual input with the way the user is moving their head. This synchronization is necessary to avoid motion sickness that results from a time lag between when the user moves their head and when the appropriate video scene is rendered. This time lag is often called motion to photon delay. Studies have shown that this delay can be at most 20 milliseconds and preferably between 7 to 15 milliseconds in order to avoid the motion sickness problem. So taking 20 milliseconds as the upper bound on the available time budget, let us take a look at the time available for each of the processing tasks for an AR/VR use case such as ours. Next slide, please. So out of these 20 milliseconds, display techniques, including the refresh rate of write displays and pixel switching, take 12 to 13 milliseconds. This leaves 7 to 8 milliseconds for the processing of motion sensor inputs, graphic rendering, and the RTT between the AR/VR device and the edge. There are some mitigating strategies that have been used to deal with the problem of motion sickness. Let us take a look at them. Next slide, please. One way is to use prediction techniques to mask latencies. Another way is to offload these computationally intensive tasks to edge devices. Emerging 5G standardization efforts by the 3GPP target an ultra-low latency of 0.1 milliseconds to 1 milliseconds between an edge server and user equipment such as AR/VR devices. Next slide, please. So that was our update. In the last working group meeting, several people said that they were willing to help review and provide input to the document. So we would like to take this opportunity to invite reviewers and contributors to improve the draft. As a starting point for a discussion, we would like to capture and document the current understanding of operational deployment requirements for AR/VR applications, such as our use case. This, of course, goes beyond the current focus of the draft, which is on ABR algorithms. These issues could include, but are not limited to, documenting the design space of application mechanisms that deal with operational issues in practice for AR/VR applications. These could be, for example, client buffering, adapting media quality and playout, prefetching, etc. Similarly, documenting the design space of system-level techniques in practice for AR/VR applications, such as using edge cloud designs like CORD, protocols and architecture suitable for the so-called contribution and distribution networks for the acquisition and delivery of AR/VR media, impact on design of overlay networks like CDNs. So we welcome other pertinent issues that the working group would like to include in the draft. And with the chair's permission, we would like to open the floor for a discussion. Thank you.
So, by way of background, I will remind people, as Renan did, that when we discussed this document before and agreed to take it on as a working group document, it was with the understanding that there were people involved in the working group who were willing and interested to review and contribute. So I think this is a nicely set up opportunity to give some particular input, although if you have feedback to give other than on the particular areas that the authors have asked for, I'm sure that would be welcome as well. There, I've given everybody enough air cover to think of their questions. Who would like to jump in with some input to the authors? Or has everyone actually secretly run away from their computers to get tea? I'm mildly tempted to actually start naming people.
So I can't remember last time. Did we take a hum last time on who would be willing to contribute, or like a, I mean, virtual show of hands? I can't recall. We did? Okay.
And if you'll pardon my noisy keyboard, I'm going to go and dig up the meeting minutes. All right. So we were not quite so. So the poll results were 10-0 for adoption of 28 participants. We took it to the list for confirmation, which we did. And then the willing to review and contribute text, there were 9 people to 1. But we didn't capture names, sadly, except for one. So, Colin, what do you think? Not to put you on the spot or anything, Mr. Jennings. He's probably actually attending another meeting at the same time and just vaguely logged in here. Boy, some people are really taking advantage of the fact that this is not a physical meeting room. You can't walk over with a mic and beat people over the head with it. I suppose I'm not supposed to do that anyway, but anyway.
Well, I mean, in real life, you just sit in the back of the room staring at your laptop, right? That's, you know, the typical MO.
Sure.
Yeah, so I did not, so I've read the draft. I have not submitted any comments, but I will take it upon myself to set myself a deadline because, as we know, deadlines are a good forcing function.
Yes. So should we say 2 weeks sounds like a reasonable deadline for the working group to chime in? I'm going to capture some names now.
Yeah, I think 2 weeks following the end of this meeting, so maybe 2 weeks from Friday seems like a reasonable deadline for a first round of reviews.
Okay. Chris, I'm putting your confession down as a volunteering to review it.
Spencer is in the queue.
Thank you. Go ahead, Spencer.
Yeah, thank you. I was just asking if this document was in GitHub anywhere. I just looked and did not see a reference to it in the document itself, but I wanted to ask. Thank you.
No, it's not on GitHub, but I could do that. Yes.
I think it would be helpful at this point if people are willing to actually sign up to review the document. I think it would be helpful to have it in GitHub, sort of as a good balance of participation there. Kyle, I think you're our GitHub maestro, so can you?
Yeah, I was just going to say we've probably gotten half the comments that we've received on the operational considerations document in GitHub. So that's a strategy that worked well for us.
Yeah, I mean, so yeah, if you take an action for me to work with the authors to get the draft onto GitHub, that would be I'm happy to do that.
Great.
Yeah, and to
Okay.
Jake's point in the chat about it would be helpful, especially if it's in Markdown. I don't know what tools you're using to author it, but it might be worth looking at Martin Thompson's Internet Draft template that does lots of goodness if you start with a Markdown document. But we could talk about that offline.
Yeah.
Okay. Great. Thank you, Raymond, and thank you in advance to all the volunteers. I look forward to making more progress there.
Thank you.
Great.
Slight technical difficulties. Give me a sec.
Yep.
All right.
You guys hear me?
You're very quiet.
Very quiet.
Very quiet.
Settings for this device. Maybe let me take off the headphone. I'm not sure why it is.
Yeah, make sure that it's using the right microphone.
Is it better now?
It's a little bit better.
Okay. All right. Hi, my name is Li Jundong. I'm going to present this new draft on use case of packet significance difference with media scalability. This is a new draft with other two co-authors, Kieran and Richard. I want to first, before we go to the slides, the real content, I want to give a small introduction of this draft. So with the dominance of video traffic on the internet, selectively dropping packets from competing media streams could become a complementary mechanism when dealing with network congestion. It is worth to investigate which packets in the outgoing queue should be dropped to minimize the impairment to the end user's quality of experience for video streaming. Due to the various scalability design in the modern video codecs, it is not hard to observe that significant difference may exist among video streaming packets. So can we leverage this to further improve the end user's quality of experience is something that I want to bring to your attention after this presentation. So please go to the next slide. Let's take a look at those two figures from the reports. Recent studies, have shown that IP video traffic will be 67% of all consumer internet traffic by 2021, and it is up from 51% in 2016. And we can see that it will be increasingly likely that multiple streaming flows will share a bottleneck link if it exists, so which could inevitably cause network congestion. In other words, the streaming flows would compete for a network resource at the bottleneck link. Some packets would be dropped entirely and indiscriminately by the router, given the assumption that video flows would share the same priority class. Next slide, please. Let's give a closer look at the modern video codecs. So a visual scene in a video is represented in digital form by sampling in real scenes spatially and temporally. So correspondingly, the modern video codec would incorporate three types of scalability, namely temporal scalability and spatial scalability and quality scalability. So the temporal scalability refers to the scalability designed to allow the frame rate of the video bit stream to be varied using interlayer prediction. And spatial scalability represents the spatial resolution variations or differences with respect to the original image frame. And this quality scalability is also commonly referred as fidelity scalability. So each spatial layer could have many quality layers. So for example, in this scalable video coding, it divides a single video bitstream into multiple representations and layers. So it includes the base layer and enhancement layers. The video may be scaled up by adding the enhancement layers or scaled down by dropping the enhancement layers. So visually, you could see the resolution changes. So go to the next slide, please. Go to the next slide, please. So specific to dealing with network congestions for video streaming, by leveraging the variable types of scalability in the modern video codecs, the video content is made available at a variety of different bit rates. So the rate control and video adaptation methods have been proposed to minimize the possibility of network congestion. Today's adaptive streaming technologies are almost exclusively based on HTTP. So adaptive bitrate algorithm ABR is in the client side that performs the key function of deciding which bitrate segments to download, based on the current state of the network. Go to the next slide, please. We acknowledge the benefits offered by various congestion control and congestion avoidance mechanisms. But we would like to point out that the feedback and rate adaptation might not be quick enough to cope with the dropping of packets on the wire. And we know DiffServe, has been proposed to be used in managing resources such as bandwidth and queuing buffers on a per hop basis between different classes of traffic. So the internet traffic may be separated into different classes with differentiated priorities. This allows, the differentiated or treatment for latency sensitive traffic like video streaming. However, with the video traffic dominating the internet, flows of media streaming applications with the same class still compete for network resources. So you imagine that 67% or even more in the future, internet traffic is video traffic. No matter which class they are classified, those flows of media streaming application will still compete for network resources when encountering bottleneck links. So the preferences decided on the traffic class will not be effective to eliminate the possibility of packet drops due to collisions with each other. Go to the next slide, please. So what is the cost of packet dropping? We all know that, the routers treat every bit byte in the packet payload equally, which means every bit byte has the same significance to the routers. So each to be dropped packet is discarded completely. So if the transport layer protocol is TCP, so after timeout or duplicate acknowledgements received at the sender may retry to send dropped packet before the maximum number of retransmissions. So the retransmission of packets wastes the network resources, reduce the overall throughput of the connection, and of course also causes longer latency for the packet delivery that would affect the user's quality of experience. Go to the next slide, please. So with, as earlier I mentioned, there are various scalability designed or implemented in the modern media codecs. So we can see that some bits of the encoded media stream are more important than others. Like bits belonging to the base layer usually are more significant to the decoder than bits belonging to the enhancement layers. For example, here, iframes hold complete picture data and is frequently referenced by the subsequent frames, later frames. So losing the first iframe in the group of pictures would cause video picture even missing for a few seconds. And because, P frame and B frame referencing to the iframe will not be decoded or, displayed due to this loss of iframe. So iframes are most essential in the media stream in that group of pictures, which have the most effect on, perceived video quality. For P-frame, so the P-frame stands for the predicted frame. So it allows the microblocks to be compressed using temporal prediction in addition to the spatial prediction. So video scenes with low level of movement are less sensitive to both B-frame and P-frame packet loss. So a lost P-frame can impact remaining part of the GOP or group of pictures. A lost B-frame has only local effects in a slowly moving content or with large static background. So it means that, you lose a B-frame, the decoder could just ignore it. So we can probably think that, you know, the I frame is the most significant frame in this group of pictures. Or P frame, where P frame is less important, B frame may be less important than P frame if it is slowly you know, moving content. So as another example, microblocks are identified to represent objects in regional interest. Regional interest means that you're mostly interested in certain objects in the video, like you know, the football player or some movie star you like. So this is called ROI, or regional interest. So those microblocks that are identified to represent objects in ROI or region of interest are likely more important than any other microblocks of the non-ROI regions to the end users. So for packets carrying ROI microblocks in the media stream need to have higher priority to be retained compared to other packets carrying non-ROI microblocks. So let's go to another slide. Next slide, please. Let's go back to the end users perspective. Okay, what the end users would prefer. So from the perspective of end users experience and users expectation, a few observations could be easily made. So it is very likely a user may prefer to acquire the media content in somewhat degraded quality that is above the tolerance threshold rather than getting nothing at all for a few seconds. Or a user may be particularly interested in certain group of blocks belonging to interested objects in the video content ROI, which is what is named. So it is necessary to prevent ROI blocks from being lost during transmission. Here, I don't know if you can see the resolution difference for this stock picture. On the left side, you know, it is original picture which is transferred through the network. Instead of getting nothing versus degraded quality in resolution, maybe the end user would prefer that, you know, receiving something in lower resolution instead of getting nothing, or it received the ROI blocks, but some of the background is missing, is fine to the end user instead of getting nothing at all. Okay, go to the next slide, please. So what if the end users can reveal their preferences to network? For example, the degree of tolerance to the decoded media content quality degradation, which might reflect visually as the resolution reduction, or some missing objects in the non-ROI regions. The network could selectively drop packets in a differentiated manner according to such information. So this could avoid retransmission or delay of those packets with higher significance, and also could reduce the experienced end-to-end latency of the end users, and could maintain the continuous streaming of the media. This is actually achieved at the cost of dropping those lower significance packets. So in order for the network to be able to treat packets of media streams in a differentiated manner and at finer granularity than diffserv, so the application share reveal some of the information to network to enable this selective packet dropping. For example, you know, the receiving end user's preference on the media quality, or some labeling of the packets, or some parts of the packet that correspond to receiver's interests objects as ROI, or some characteristics of the media content containing the packets. For example, the frame type, or its I frame type, or B frame type, or P frame type, or some movement level, if it's a static background or it's heavily moving picture. So those information would help the network to decide which packets may be of higher significance than the others, and then those selective packet dropping could happen in the network. All right, let's, I think, go to next slide. That's the end of the slide. So, I welcome any comments and suggestions on the document.
Thank you very much, Li Jun. So, any questions? I see there was chatter in the
We
chat
have someone
room.
in the queue. Kirill is in the queue, so I recognize Kirill.
Hey, thanks. I have a question about the macro blocks. I'm not aware if they're exposed anywhere, like to container or to like even application layer.
No, let's relate it to the codecs, like how the application could provide some metadata information or some information about the blocks that contain in the packet payload. So it's not like the micro blocks will be seen in the network. It's just some information about the micro blocks containing packet could be revealed to the network. That could help to decide whether this packet is more significant than the other packets in the outgoing queue.
Yeah, no, all right, I got that. But in order for someone needs to tell, like, hey, this packet contains microblock, and for that, so someone to tell that, codec actually needs to expose that information somehow, right? So then, like, whatever we use today for video delivery, like most of the time it's HTTP and like some dash or progressive containers MP4s, right? So there is no information in there. So like that part seems to be missing.
Yeah, that's correct. So that's why we think there could be some way to incorporate this information at the application layer from the source. That could help with this, and then it will be seen in the network layer as well. I think. Mm-hmm.
Yeah, I have another observation. So you mentioned that in presentation that like information at packet level like would be useful, so like we can selectively drop it at routers and so on, right? I wonder if we can actually leverage what we have today in transport, right? So Quick, for example, seems to be already provide this capabilities, like they have datagrams. So you can, for example, put PB frames on datagram and iframe on a quick stream, and then you basically get a reliable iframe delivery guarantees, and everything else is going to be not like it's a little bit like with like different guarantees, right?
Yeah, that's a good implementation detail. Like, I only want to bring this concept for your attention. Like, if the network layer could have this information, whether it is implemented in Quick, some options there, or either in HTTP, that's okay, or even in the network layer. So any implementation wise detail could be discussed later, but I want to bring your list to your attention that the application layer, some of the information from the source could actually help the network to deal with the network congestion. We do not think that it's alternatively to dealing with network congestion, but it's a complementary way to do that, to help with fighting the network congestion.
Thank you.
Yeah, sure.
All right, Jake. Can't hear you, Jake, if you're speaking. Can't see him either. I see 0 kilobits per second. Is anyone getting Jake?
No, I
Yeah. Okay. Here we go.
There we go.
Better?
Okay.
All right.
Yep.
It gave me an error, and then it said it was retrying. All right. Great, thanks. Yeah, I guess, is there a proposed API for this, or a paper, or a draft, or something?
No, this is the first draft about the, the observation of the, media streaming, what the scalability of the media codecs that could bring some new aspects of, how to selectively drop packets at finer granularity than the traffic class level. So I haven't gone into the paper drafting or anything else yet, but definitely that's the next step I want to do.
Okay,
If
great.
you are interested, then I will definitely send you the paper when it is on public.
Possibly. I guess you mentioned diffserv. I'm not sure which use cases you had in mind, but in cases where diffserv is appropriate, I think you already can set. So if you're sending a UDP stream of some sort, or RTP or whatever, if you have access to the macro block information, I think you can set diffserv differently for the different packets that you're sending. The APIs to do this would be just a sock opt, I believe. So I'm not sure if that will meet your needs or not. Certainly for streaming to end users, that's going to have some trouble.
Yeah.
But
we can have a little more detailed discussion with you. I think, yeah, that could be one way of implementing this. If you think there is a way of adding the, differentiating different packets in different flows with the same class, then maybe that's a way of implementing it as well.
I meant more like different classes in the same flow.
Right.
I don't think you have any.
Different classes in the same flow. You mean using different classes for the different packets in the same flow?
Yep.
If that's an option, we can definitely dig into that. Yes.
Yeah, thank you. That's it.
Yeah, sure. Thank you, Jack.
So we have Spencer, and then I think we're going to close the line there so we can move on to our next presentation. Go ahead, Spencer.
Yeah, I think that we're either talking about we're either talking about something that is outside the quick payload, which diffserv would be if that would work, or something that gets added to a quick public header. If I'm understanding this correctly, unless you, and my point is, unless you're terminating a quick connection someplace in the network and regenerating it on the other side of that. I mean, that's actually a conversation that we could have. But I think that there's a real fundamental conversation to have about how this is going to work, because if you're not, if you are trying to do this based on quick packets, anything that's running over HTTP, which a lot of streaming media does, is going to have a lot of stuff in a quick packet that you can't read unless you're terminating it. It seemed like to me, but I'm sure we'll talk.
Yeah. So thanks for the comments. Yes, I think I want to have this kind of conversation going on, because I haven't looked into the detail of the the up layer protocols, which one to use. Like, for example, you mentioned the quick, and there are any limitations for this concept to be implemented in body of the quick as the application layer protocol, so, or transport layer protocol. So I think that's something we can discuss more and see. The only intention for this document or presentation is to bring your attention to maybe this is something we can leverage, from the perspective the end users preference, and then what if the application could provide more information about the packets or the package payload, then the network could actually fight the network congestion better than right now. And then there is no packet dropping, maybe some slight packet dropping, but not severe packet dropping. So that's something I want to bring your attention, and then we can have more discussion on the solution side. Yes.
Yeah, I think that's a really, it's an important point, and I think there have been some efforts in the past to do more of this sort of application network transport information awareness sharing, but as you point out, there's so much of the internet today, so much of the traffic on the internet today is for video, that we really do have to figure out a better way of handling this. So I think it's interesting stuff, and I think the biggest challenge really is to get people who are aware of applications workings to work with people who are aware of how networks work, and figure out how to get them to talk together without violating the various
Yeah, that's very true. Actually, it must have the help from the codec side, to understand what is included in the packet payload, and how the codecs work could help with the network understanding what is going on in the packet. So I think definitely that requires two types of expertise, maybe that is lacking in the IETF about the codecs, but I hope that we can bring some of the liaisons, or maybe something, some experts here, just to help with the codec side. I briefly have some readings about MPEG and H.265. So those codecs are actually designed in a way to provide scalability, which amazes me that it's actually helpful with the packet dropping decision to make.
Great. Spencer, you're not done. You're still in queue. Oh, Spencer's out of queue. Okay, that's great. Thank you very much. And please do share, onward materials with the Mops working group. We'd be happy to hear thoughts and questions as they evolve.
Okay. Yeah. So
Thanks.
What is next step for me? Like, do you think?
So if you could, you had mentioned you have a paper that you might be able to share. If you can join the Mops working group mailing list and perhaps share information there, hopefully we can get more discussion and pointers to, appropriate things to follow up in the IETF context.
Okay. All right. Sure. Definitely. Thank you so much.
Great. Thanks. All right. So, Kirill, if you would be so kind.
Hello. Can you guys hear me?
Yes.
We can.
Awesome. All right. Hi, everyone. My name is Kirill Pugin. I'm going to talk about the draft that we published a couple of weeks ago, and it's about reliable, unreliable streaming protocol. It's actually a little bit related to the previous discussion we just had. Next slide, please. All right. So first, I would like to kind of cover a little bit of motivation why we decided to build something new. First of all, like for live video streaming specifically, there's a lot of different use cases and different requirements. In some cases, latency is important. Some cases, quality is more important. So, like for example, live streaming of soccer match may be okay with 10-30-second latency. However, interactive streams like game streaming would benefit from really low latency. And 5 seconds is not really low, but it's can be good enough. We also wanted to be more extensive, support extensibility, like new audio-video codecs, have some sort of RPC-like mechanism so we can implement client-server interactions, support multi-track, including captions. Next slide, please. We also, really important topic was reliability. A lot of our use cases are on mobile devices, and people on mobile migrate from cell to Wi-Fi network between different cell towers. They also drive through tunnels, so and in general, network conditions changing over time. That's one part of reliability. However, the other part of reliability is in order to actually ingest live videos at scale, there is a lot of pressure on the server infrastructure, and so in many cases, server need a way to go on maintenance and how to do that in a graceful manner so clients can actually gracefully reconnect was important aspect of this work as well. Quality, super important as well, and having actually better signals from network layer to adjust to provide audio-video bitrate selection and match them to network conditions is super important. So that's one of the reasons we actually was trying to build this, utilize the new transport protocol QUIC for this work. Next slide, please. So there are obviously a bunch of different protocols exist today. So like RTC has a lot of flexibility, but its primary focus is on peer-to-peer or video calling experience. So it's in my mind, it's a little bit more latency focused. So it's a little bit harder to more difficult to do trade-offs, and it's pretty complex. So RTMP, that one that we had running, and it was not very flexible, so like no new codec supports. Some implementations were like not even supporting reconnects. Other type of protocols that like HTTP based, like Dash or CMF ingest, does not allow per frame control, and so it makes it hard to control the latency. Next slide, please. So what is Rush? So Rush is a bidirectional application level protocol designed for live video ingestion, and it's designed to run on top of QUIC. We do support fallback on TCP, but QUIC is much more preferable. It was built as a replacement for TMP with the goal to provide support for new audio-video codecs, extensibility, multi-track support. In addition, it gives application option to control data delivery guarantees by utilizing QUIC streams. So as in previous presentation, we discussed the importance of iframe and PNB frames may be less important. This actually allows us to provide different delivery guarantees based on frame types. Next slide, please. At core, it's a frame-based protocol, so client and server exchange frames or messages. We can call them messages as well. And each frame has a common header, which consists of length, ID, and type. Next slide, please. So length just determines the size of the whole frame. ID is a frame sequence number. So each frame is actually have a sequence number, and every new frame must have a sequence ID greater than the previous one. And the type is just to differentiate different type of the data. Next slide, please. We define 7 frame types, but obviously they can be extended. It's a connect frame, connect acknowledgement, end of video frame, error, audio, video, and go away frame. Next slide, please. So Rush actually defines 2 modes of operations, normal mode and multi-stream mode. In normal mode, we use one bidirectional QUIC stream to send and receive data. So using that one stream guarantees reliable in-order delivery, so applications can rely on transport layer to retransmit lost packets. So that performance and behavior is very similar to just using TCP connection. Next slide, please. So in normal mode, client sends a connect frame on bidirectional quick stream and then continue sending audio and video data on the same quick stream. We only support one video being sent on one connection. Server, upon receiving connect frame, replies with connect acknowledgement. Connect and connect acknowledgement is a mechanism to sort of negotiate the features and versions of the protocol. So if server doesn't support something, it can basically reject that. Because we use this one single quick stream in this mode, frames arrive in order, so server doesn't need to worry about reordering data and making sure that no data is lost. That is transport layer guarantees. Client send, once client is done streaming, it sends end of video frame and close the quick connection. So pretty simple. Next slide, please. So one of the problems in this mode is that if one of the packets got lost and let's say it belongs to V2 frame in this diagram, so then all the frames that are sent after it will not be available to the server, like not visible to the server. They still potentially can arrive at transport layer, but Quick would not expose them. And so until V2 is actually transmitted and fully received, so server cannot do anything. So this is sort of variation of head-of-line blocking, and it can affect latency, introduce jitter, and so on. Next slide, please. So multi-stream mode is essentially tries to address head-of-line blocking and also gives application much more control over delivery guarantees. So in multi-stream mode, every frame, every new frame, audio or video is sent on new quick bidirectional stream. Since quick streams are independent from each other, this allows server receive data as it arrives and not wait for retransmissions of lost packets on unrelated from unrelated streams. Next slide, please. So in this mode, still client creates on existing connection, quick connection, creates a bidirectional stream, sends a connect frame, and creates a new stream for every audio or video data. So because, as I said, we use different streams, frames arrive out of order, so server needs to be able to restore that order, and it can use frame IDs for that, as well as to detect if some frames are missing. Client can stop retransmission by essentially resetting the corresponding quick stream. That way, it can provide set different delivery guarantees depending on frame type. So, for example, on iframe, we can always retransmit PNB frames. We can set a timer and reset the quick stream after the timer, and therefore we just stop retransmissions. Next slide, please. So I talked about a little bit reliability and being able to reconnect. So reconnection is can be triggered by the client or by the server. In case of client, it's usually when connection got lost, either because we drove through the tunnel or some other reasons. So in this case, clients open a new connection and they close the previous one and continues with a normal connect flow and continue sending data on a new quick connection. Next slide, please. In case of server initiated reconnect, server sends go away method frame, and client may send frame up on the current connection even after server sends go away. That's usually useful and somewhat required to drain the existing gulp interval. So otherwise, the data is going to be lost. So client establish new connection and follows a normal connect flow and continue sending data on new quick connection. It's up to the server whether to close the connection immediately after sending go away. Usually, it's preferable so server doesn't close connection right away and allows client to send existing current gulp size. Next slide. I think that's probably it. Questions, and can we move to the next slide as well? We have side meeting on Friday. If anyone interested to join, we'll be happy to answer additional questions there as well. Thank you.
Great. Thank you very much, Carol. We have a queue. James. I'm not hearing James unmute. All right, if James is being shy, how about Hasham? People think they want to ask questions.
Maybe there are some technical difficulties.
I have two questions. First one,
Okay,
do we have documentation for push?
Documentation for push, what do you mean?
Like specifications or paper? Or...
Oh, for Rush? Yeah, there is a
Rush,
draft.
yeah, Rush, sorry, Rush.
Yeah, there is a draft that we published a couple of weeks ago. I think it should be in the meeting materials. If not there, I can send a link.
You can put it in the chat or something. The second question, does Rush use Kuba congestion control?
So congestion control is basically a transport layer, right? So because we use Quick, we use whatever Quick provides. However, in our deployment, so the beauty of Quick, you actually can change congestion control, right? So, and that's because it's all an application layer. So in our deployments, we used BBR, we tested Cubic, we tested COPA as a congestion control, and there was a presentation at Congestion Control Working Group in Singapore a couple of years ago or a year ago that kind of provides a lot of information about the performance comparison amongst three of those. We use right now, I believe, BBR and COPA as a congestion control.
In addition to Quick.
So Quick is itself, right? So it's Quick is UDP-based protocol, right? So, but it does assume there is a congestion control, right? So we, as Raj does it on its own, does not specify congestion control. Congestion control is implemented at transport layer, at Quick layer, and it just it happens so that we have multiple implementations. And yeah, by the way, actually, we also did another test disabling Quick congestion control at transport layer and implementing it at application layer using RMCAT. That was also we have results for that as well. Same Singapore meeting.
Maybe you can put in the chat the link to your draft for Rush.
I'll send the link in the chat thread if it's not there.
Okay, thanks. And I think James said his question was answered, but Jake, go ahead. Uh-oh.
There we go. Working?
Yes.
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 Okay. I think I did see this draft. It seemed like it had a lot of kind of video specific stuff in it. Codecs and references to audio versus video versus and these were quick extensions if I remember right. have you thought about making it more generic? Again, here I'll point to SRT as a like. Yes, there are things that so the one feature that keeps sticking in my head is the way that you can say it's reliable as long as it's before a deadline. It's after a deadline, then you drop it instead, so that you don't do the headline blocking. You don't do the so like, are there features like that that you could embed into Quick in a sort of transport feature sense, rather than doing it as like, this is video, this is audio, and then treating it that way?
So let me answer our first question about like making it more generic. It's so the audio video specifics are there, but they're like actually like at high level, the whole thing is pretty generic. Your frame can be anything, right? So it can be, you can send text file inside of the frame. So, and it's up to you as a application to specify delivery guarantees on that frame, right? So you can set a timeout, basically deadline delivery, right? So if it's not delivered, just stop retransmitting. To answer your question around Quick, yeah, I would love that. I think the Quick went in a little bit different direction. So they introduced Quick datagrams, right? So where essentially like there is no guarantees, right? So so they're gonna get dropped, and that's it.
So this is all over datagrams, you're saying? Okay.
So this one, this is our implementation does not use Quick datagrams because it was developed and deployed before Quick datagrams were even introduced or proposed as a draft. It can be built. I think in my mind, the diagrams are. It's just gonna be more work for application, because you still need to you still need to control retransmissions, right? So then how it interacts with congestion control, and it's something that QuickStream seems to provide out of the box. So it just seems a little like simpler in terms of implementation of the whole thing.
Okay, so was this like there was a priority of audio over video or some such? Was that the?
So I'm just going to interject here that there are still people joining the queue. Well, yeah, it might be better to take it offline. We're actually now over time. I asked Kyle to put the milestones slide up because this was supposed to be our last agenda item. We're not going to get to it. So I'm going to say last two questions in the order that they were there. Maxine, you can come back. Thank you. But we will take the milestones discussion to the list, and we'll do these last two questions in order as long as the Meet Echo doesn't disappear on us. So, Shui?
Two questions, actually. You mentioned new codec support. Just wondering, in what perspective Rush going to support a new codec? The second is regarding live streaming. What kind of application layer protocol you are mainly referring to? I will believe it's going to be HTTP.
So live streaming in this case, that was ingestion, right? So it's, but there is also desire, thinking on our side is to essentially what we want. I think the future is for us is to have ingestion and delivery protocol similar, right? So like actually be the same. We're not there yet, so our ingestion was the first attempt. Can you remind me the other question that you asked?
The live streaming protocol. I was wondering if only the HTTP is the one you are referring to, or you have another like RTP in mind as well.
I'm sorry.
Is it just HTTP? Is it just HTTP, or do you have another protocol in mind?
On delivery side, I think HTTP is just so widely used that we're gonna have to stick to it. But kind of enhancing it and figuring out how to do this unreliable delivery on top of HTTP, that's something that's, at least I think it would be interesting. HTTP by itself is not bad, especially with HTTP3 with Quick is like, there's a lot of things that are useful. And existing infrastructure that already been deployed in so many places.
Okay, thanks. Maxime, take us out.
First of all, thanks for the great presentation. There was a topic of secure reliable transport protocol raised during the discussion. So from the secure reliable transport protocol, I would like to say that we are also evaluating Quick datagrams and SRT over Quick datagrams streaming. And the main benefit of datagrams over reliable Quick, as we see it, is the ability to control and manage the latency. Because even if you want something to be delivered reliably, you still have certain latency. And if your iframe gets delivered, for example, 1 second late, then the whole your stream is blocked for 1 second. So that's something we would also present on the Friday side meeting, video interest of Quick. So if someone is interested, please join. We'll have some discussion there. Thank you.
Okay. Any reactions, Carol? No? Okay. Great. Well, then.
No, yeah, I can, I think I address that. I don't think datagrams or quick streams necessarily different in terms of latency. At the end of the day, Quick underneath is built on top of UDP, so it's the same. I think the difference between datagrams and streams are the reliability, like the actual retransmissions by default, right? So datagrams do not have retransmissions. However, it's a question whether what is the best default mode? No retransmissions or retransmissions up to some certain point, right? So, and as I said, in my mind, streams are a little bit easier to work with, but again, I haven't explored much datagrams yet, so I'm happy to discuss on Friday more.
Yeah, that is completely true. Just when we go to sub-second latencies, you really need those reliability part to be handled on your own. So that's the main question here. But for certain use cases, also reliable mode would also work.
Yep. Great.
Great. All right. Thank you, Kirill. Thank you all for the questions. Thank you all for saving us from a milestones discussion. And again, thanks to our meeting minutes takers. Yeah, thanks everybody for coming out and making it a lively session. We'll see you online or in person in a few months. Certainly see you on the mailing list.
All right. Thanks, everyone.